Hey guys, this particular video is going to be dedicated to solving for the moment of inertia of a rigid bar rotating around one of its endpoints. So let's say that we've got this rigid bar just here, right here, and it's a three-dimensional object. I know I'm not much of an artist, but it's a three-dimensional object just here, right? And it's rotating around one of its endpoints. So I'll even draw a line just here to show you what it's rotating around. So it's just rotating around there. It doesn't matter if it's clockwise or anti-clockwise. Either way, it's rotating, right? And I'll even draw that as well. So it's rotating around this point. And my question to you is, what's its moment of inertia? Now, to do this, we need to refer back to our definition of our moment of inertia. Recall that we've got two formulas. One of which is for discrete masses, which is the moment of inertia is equal to the sum of mr squared, right? But this is really for discrete masses, so for like a whole bunch of different chunks of mass rotating around an axis of rotation. This doesn't, well, it could apply here, but it would only apply in an approximation, right? It would be much better to use this definition. I is equal to the integral of r squared dm. They're very similar, but this is perfect for a continuous body, i.e. a body which isn't consisting of a whole bunch of smaller chunks. We could, however, use this as an approximation by assuming that there are a whole bunch of different chunks that make up this bar, right? But that would just be an approximation, and we're interested in the exact answer. So let's do that. Let's follow this formula right here. To do this, we're going to need the assistance of an axis. So I'll just create an axis right here. I will call this right here our y-axis. I will call this right here our x-axis, and I will call this right here, going into our page, our z-axis right there. Okay, and my question to you is, what is the moment of inertia? Well, in order to do this, the first thing we need to do is, it's not a free body diagram this time, it's create an element within this bar. So I'm going to choose to find the volume of an element somewhere along this bar, and I'm going to choose an element just like this, a distance x, an arbitrary distance x from our axis, right? And so if it's an arbitrary distance x, and this is a small little chunk of your bar, an element even, that means that this distance here, right, that small distance is going to be dx, meaning that the volume of this entire element, just imagine shading that in, the volume of this entire element is going to be dv, but it's also going to be equal to dv times by dx times by whatever this height is, I'll just call it c, times by whatever this base is, I'll call it b. Right? So in other words, we can say that our volume is, remember, it's length times base times height, which is dx times b times c, meaning that, and let me just write that down here so it's a little bit more clear, that means dv, our volume of our element, is dx times bc. Okay, this may seem a little bit unconnected right now, but it's really crucial because we can use this formula right here. We can use the formula that the density of any object is going to be equal to dm dv. This is a fundamental truth right here. This is true for even non-homogeneous objects, right? And the crucial part about using this formula is we can arrange this to solve for dm. So we can say that dm is just equal to rho dv, right? And let me scroll down a little bit so you can see. In fact, let me zoom out a bit. There we go. So we can actually write now that dm, the mass of our small element, is just going to be equal to rho times dx times bc. Right? This is crucial because we can plug that now back into this just here. Let me write that out. I is equal to, your moment of inertia, the integral of r squared dm, right? And we just found out that dm was equal to, what was it? It was rho dx bc. Right? Notice that in this case, b and c are constants, right? And if we assume that this bar is made of the same material everywhere, like it's all steel or it's all wood or something like that, that means rho is constant, the density is constant. So we can take that outside of the integral sign. So we can write that as rho bc times the integral of r squared times dx. Well, what's r? Recall back to the video I did on moments of inertia. R is your distance from your axis of rotation towards your element of mass dm, which was x. Remember, the x is our distance from our axis of rotation towards our element, right? That's what I mentioned earlier. So that means r is just equal to x. R is our distance from our axis of rotation to our element of mass dm. So we can now write that our moment of inertia is just going to equal to rho bc times the integral of x squared dx, right? Now here's the interesting thing. What are our limits of integration? Well, our limits of integration are defined by the not only this term right here. Well, because this is dx, that means our limits of integration will involve our range of x values that make up the bar. Notice that I've defined my axis to be here, and the range of x values that make up this bar is from x is between 0 and L, right? Where L is the length of our bar. I should have made that a little bit clearer. L is the length of our bar, just here. Right? So in other words, the range of values that make up our bar is x is from 0 to L. So I'm just going to use those limits of integration, 0 to L. Right? I hope that makes sense. So if we evaluate that, we can write that our moment of inertia is equal to rho bc times by, well, what will be? It will be x cubed on 3 after doing the integration, with limits from L to 0. Do the little bit of substitution, and we're left with rho bc L cubed on 3. This is our answer, but it's not a neat one. We've got b's and c's and rho's in here. Maybe we can find an easy way to simplify this, and indeed there is. If we assume, like we did earlier, that our density is constant, that means that our density is going to equal to our total mass over our total volume, right? So our total mass over our total volume is equal to our density if the density is constant. Okay, so we can now simplify that to write now that our mass is equal to our density times by our total volume. But we know that our total volume is, and let me draw it over here, we know that our total volume is just going to be, what is it? Well, this is L, this is B, this is C. Our total volume is just going to be equal to LBC, right? So that means we can write our total mass is equal to our density times LBC. Okay? So that means that we can, and this is crucial because if you notice, our moment of inertia can be split into rho bc times L squared on 3, right? So we can simplify this by writing mass times L squared on 3, right? That's using this just here, right? Meaning that our moment of inertia now finally is just equal to mL squared on 3. This isn't for any rotating object, this is just for a bar rotating around one end. And notice the consistency here. Moment of inertia has units of kilograms meters squared, if we're SI units anyway. Alright, thanks guys.